In the last video we covered the top three here, which gave us the inverse sine function. Now we're going to cover the bottom three, and this is going to give us the inverse cosine. Now before we go ahead and look at the mathematics, let's go on to the graphical calculator and we'll see the simulation. Now we're going to go through a similar process that we did whenever we worked out the inverse sine. We're going to pick a particular point. So here's the point here. Now in this instance here, what you have to imagine is that you've got two pieces of information. You've got the x coordinate of the point, so that's the 0.866, and you've also got the length of this line here. So those are the only two pieces of information, and we're trying to find this angle. So we could say that the length along here is going to be the adjacent. So we're going to have the length of the adjacent here, which is this 0.866. And we're also going to have the length of the hypotenuse. And the hypotenuse is this length here. So that means we're going to have the adjacent and the hypotenuse. So the adjacent over the hypotenuse gives us the cosine function. And we're looking to turn the lengths into angles. So we're looking at the inverse cosine function here. Now instead of starting off with a vector which lies along the x-axis, now we're going to start off with a vector that lies along the y-axis. So that's this little pink vector here. And the distance along the x obviously is 0, and the distance up the y-axis again is going to be this scaled size, which is 0.6072. Now what we're going to do is compare the x distance of this vector here with the x distance of the blue vector. So we start off by noting that the x distance of this vector is simply a value of 0 at the beginning. Now that's going to be less than the x value for this vector here, which is going to be 0.866. So what we're going to do is we're going to rotate this vector here at an angle of our first angle, which is 45 degrees. So you can see now that after rotating this, we've now got an approximation for this distance here, 0.866. And our first approximation is 0.607, so that's this distance. So all we've done here again is a pseudo rotation. So we've rotated this point in effect to this point, but we've also got the scaling by our cos of theta, which takes this point here to this point here. Now again, we compare this distance here to the x distance of this blue vector, and you can see it's still less. So we're going to have to rotate again, and again we rotate by our second value here, which is going to be our 26.565. Now that we've rotated it to this second point here, we then look and find the x distance. You can see the x distance here is 0.911, and it's going to be greater than 0.866. So we're going to have to rotate it in the opposite direction with the next approximation. So our next rotation angle is going to be our 14 degrees. And again, you can see now that the point is 0.835, which is less than the distance 0.866. So we're going to have to rotate this in the opposite direction. So I'll go ahead and I'll do the rest of these rotations now. So finally you can see the approximation that we have made. So the correct x distance is 0.866, and our approximation here after our 9 iterations is 0.8645. So in this example we've been given two values. We've been given the x distance here, which is the adjacent, which is 0.866. We've also been given the length of the hypotenuse here, which in this simple example is just a value of 1. But of course we've had to take this value of 1 and we've had to scale it back to a distance 0.607, which was the distance of the original vector, pink vector, which lay along the y-axis. So in effect we've got two values. We've got the adjacent and we've got the hypotenuse, and from those two values we're able to add up all of the little angles, add and subtract the little angles to get the final angle. So therefore we've gone from a distance to an angle using the opposite, using the adjacent and a hypotenuse. So we've formed the inverse sine function. Now one thing to note, that whenever we add and subtract all of our angles, we're not going to be left with the value for our 30 degrees. We're actually going to be left with the larger angle, which is from the y-axis down to this point. So we're going to be left with actually 60 degrees. So we're going to have to make the initial value Z0 for our angle is 90. So it's going to be 90 minus this value of 60, which will give us the angle of 30 degrees. So I have returned everything to the initial values. So you can see at initialization we're going to have the value x0 is equal to 0. So this vector here doesn't go along the x-axis. And we've got the y0, which is given again by 1 upon an, which is our k value, which is approximately 0.607. So we've got this vector here, which has got 0 in the x and it's got 0.607 in the y. Now the value for our z0, the initialization angle, is going to be the angle of 90 degrees. And our value for our x in is just some value c. Now in this instance here, for this example, the value is going to be 0.866. So that covers the initialization. Now if we look at the output values, the final value for our x is going to be the value c, which in this example is 0.866. The final value for our y, which is this distance here, again by Pythagoras, is going to be our value for our hypotenuse squared minus the value for our x distance squared. Now the value for our x distance here again is just the value c. In this example it's 0.866, and you can see that the value for our hypotenuse here is this distance here, which is the initial y0 height times the scaling factor an. The value for our angle here is going to be the initialization angle. So in this instance here, the initialization angle is 90 degrees, and we're going to be adding on or subtracting off the arc cosine of our x distance here, which is our c, divided by our hypotenuse, which is going to be our an y0. And we've seen how we worked out an. Again, it's the same as in the previous example. Now in this example we have the plus and minus here again, and we determine the plus and or minus depending on the sign of the x value. So for instance, in this example the x value is positive 0.866, therefore we're going to take 90 and we're going to be subtracting off that value. Now if for example this had been round the other side, so for example if it had been say we had gone to 150 degrees, so in effect this is going to be 30 degrees and this would be 150, then what we would be doing is we would take our 90 degrees and then we would add on this value here in order to get the final angle. So we're going to be working in quadrants 1 and 2 with this rotation. So it means that if we actually had inputs which sat in quadrants 3 and 4, then what we could do is we could take the quadrants 3 and 4 and we could use some trig identities in order to move them into quadrants 1 and 2. But we'll see that in a different video. we're going to run into the same problems that we ran into with the sine function. That is, we're going to have dead zones. So in this instance here, if the value here for our vector is getting close to 0 degrees, so let's put it at 2 degrees, then you can see that as we move this round, in order to make the approximation, we're going to add the 45 on, then the 26.5, and then the 14, and again we'll add the other value on here, which is the 7.125. But when we add the 7.125, we've actually gone to the other side of the circle. So this distance here out to this point here, so this is the x distance, 0.9959, is going to be less than the actual x distance here, which is 0.9994. So it means that instead of taking this point here and rotating it back this way, the algorithm will now continue to move this point round in the wrong direction. So now we're going to move it this way here, instead of moving it this way here like we would want to. So again, this is the same type of problem we had with the sine function. There's going to be a little dead zone, and again the dead zone is going to exist over in this side here whenever the angle is going to be close to 180 degrees. But that's more detail than we need to get into in this course. It's just a note to show you that there are issues with the simple CORDIC algorithm, but there are other ways of fixing or mitigating these issues using more complicated CORDIC algorithm structures. But we'll maybe get into that in an appendix section at the end of the course. So that's all for this video. Now we've covered the three basic inverse trigonometric functions: the inverse tan, the inverse sine, and the inverse cosine. So what we want to do in the next section is cover the functions for the sine, the cosine, and the tangent. And we're going to do that using something called rotation mode. So let's go and we'll cover that in the next section. Thank you for listening. I'll get you on the next video. Goodbye.